everyone, I'm Sam. Today, let's learn the basic principles of IEEE 1588 time synchronization.
This animation describes the applications and principles of IEEE 1588 v2 feature. IEEE 1588 version 2, IEEE 1588 v2, is a precision clock synchronization protocol for measurement and control systems. IEEE 1588, also called the Precision Time Protocol, PTP, can achieve a time synchronization accuracy within the sub-microsecond range. Mobile networks such as CDMA and TD-LTE networks require high-precision time synchronization. Conventionally, the networks obtain time signals from the GPS. However, the cost for deploying a large number of GPS devices is high, and GPS satellite signals may occasionally be blocked. The IEEE 1588 v2 function can be enabled on transmission equipment to achieve high accuracy time synchronization. Therefore, this function can replace the GPS to provide time signals to base stations. Clock synchronization includes frequency synchronization and time synchronization. The IEEE 1588 v2 protocol mainly applies to time synchronization, although it can also be used for frequency synchronization. For two devices between which frequency synchronization is achieved, the pulses of clocks are at the same frequency and keep a consistent phase difference. For two devices between which time synchronization is achieved, the pulses of clocks are at the same frequency and have the same phase, or the phase difference is negligible, and the time indicated by the clocks is measured in the same timescale. If time synchronization is achieved, the slave clocks trace the master clock. Therefore, the clock tracing relationship of a clock synchronization network is like a tree, with the root node being called the grandmaster. Clocks that support the IEEE 1588 protocol are also called PTP devices. PTP devices can be classified into OC, BC and TC nodes. An OC node provides only one PTP port. A BC node provides multiple PTP ports. A TC node can process and forward IEEE 1588 messages but does not synchronize with other PTP devices. The RTM products determine the master-slave clock hierarchy using static clock source selection, or BMC algorithm. Static clock source selection means manually specifying clock tracing relationships. The BMC algorithm automatically generates a clock tracing relationship tree based on information such as the number of link hops and clock quality. Any time of a slave clock corresponds to a local time TS1. If a local time TM1 corresponding to the master clock is known, the time offsets between the master and slave clocks can be calculated using the following formula. Offset equals TS1 minus TM1. The slave clock calibrates the local time using this offset. In this manner, time synchronization is implemented. The time offsets between the master and slave clocks is represented by offset, and the message transmission delay between the master and slave clocks is represented by delay. Offset and delay can be obtained through the transmission and reception process of two messages. The transmission and reception process is as follows. The master clock transmits a sync message at T1. The slave clock receives the sync message at T2. Therefore, T2 equals T1 plus offset plus delay. The slave clock transmits a delay request message at T3. The master clock receives the delay request message at T4. Therefore, T4 equals T3 minus offset plus delay. The master clock sends a delay response message to inform the slave clock of the information about T4. The slave clock calculates offset and delay using T1, T2, T3 and T4. The network-wide time synchronization solution enables all PTP devices and service devices to synchronize their time with the same reference time. A network where time synchronization is implemented across its entirety has the following characteristics. PTP devices are OC nodes or BC nodes. Time signals are recovered and transmitted among PTP nodes one by one. PTP nodes support clock source selection and protection switching. For example, if the PTP link between BC2 and BC3 fails, BC3 receives time synchronization information from the PTP link between BC4 and BC3. When multiple time domains share a PTP network, IEEE 1588 v2 time signals need to be transparently transmitted. TC nodes only process and forward transparently transmitted IEEE 1588 v2 messages, but do not implement time synchronization using these messages. An end-to-end TC adds the residence time into the correction field of a message. A point-to-point TC adds the residence time into the correction field of a message, as well as the transmission delay of the upstream link. An RTN-NE can work in TC or TC plus BC mode to implement transparent time transmission. When an RTN-NE works in TC mode, it allows IEEE 1588 v2 time signals to be transparently transmitted between Ethernet ports. For transparent time transmission within an NE, the residence time of an IEEE 1588 v2 message is the delay between the ingress port and the egress port. When an RTN-NE works in TC plus BC mode, it allows IEEE 1588 v2 time signals to be transparently transmitted between Ethernet ports or over microwave links. For the transparent transmission over a microwave link hop, the residence time of an IEEE 1588 v2 message is the total time for traversing the entire microwave link hop. In this case, the two RTN-NEs, one at either end of the microwave link hop, achieve time synchronization between them through the microwave link and form a time synchronization island. The two RTN-NEs can be considered as a large TC node. A network that supports transparent time transmission has the following characteristics. All RTN-NEs along the transparent time transmission path work in TC plus BC mode. RTN-NEs transparently transmit time signals to downstream NEs through Ethernet ports. RTN-NEs can transparently transmit multiple channels of time signals. When RTN-NEs transparently transmit IEEE 1588 v2 messages, Ethernet services need to be created to transmit them.
That's all for today. Thank you.